the last class we ended with an introduction to carboxylic acids. We also talked about alcohols, right? So their general formulae and isomerism and some of the properties, reactions, combustion and oxidation. The manufactured ethanol, right? One is by fermentation, which is a batch process, and then is by the hydration of ethene, which is a continuous process, right? And now we have carboxylic acid. So just to take a look at them again, the general formula is CN H2N plus 1 COOH. And as I mentioned, right, when we are naming them, we need to keep in mind whatever number of carbons we have here with the CN plus 1 with the COOH, because that functional group, the carbon of the functional group, is included in the total number of carbons, right? So for something such as propanoic acid, where you have a total carbon count of 3, the N coming into the formula will be 2, because one of the carbons is with the functional group, right? And then similarly, and interestingly for alaikum assalam, interestingly for methanoic acid, right, N is 0, because the only carbon it's going to have is the one in the functional group, and so the right, you just have a single hydrogen attached to the functional group. Similarly for ethanoic and butanoic, and so these are the structural formulae. The book does not go into isomerism, and neither will I, because we don't want to confuse you and scare you too much. Not too much, right? We did scare you a bit. So, right, let's continue with reactions for carboxylic acids. Let me just set this. It keeps resetting every time. Okay. So now carboxylic acids are acids, and if you recall, we have actually come across these earlier on in the chapter of acids, and we were introduced to them as weak acids. Does anyone remember what the difference between a strong and a weak acid is?
Could you repeat that question?
Carboxylic acids are weak acids.
Yeah.
What is a weak acid? What makes an acid weak?
pH.
Huh?
It has a low pH.
Uh,
It's not very reactive.
it does react. Obviously, its reactions are much milder as compared to what the other types of acids, they're called mineral acids.
It's not very an active
So
acid.
HCl, H2SO4, and all these others, they're called mineral acids, right? Whereas carboxylic acids or organic acids are these guys, the
Like
ones with
its pH would be
the pH will be
near 7.
yes, it won't be as acidic, but then why would that be? So you're technically correct, but what I'm asking for is the reason. If you sort of can recall, we have talked about what makes an acid strong or weak. Do you remember the definition of what an acid is? Hmm?
Like they react with alkanes to make salt.
That is a neutralization reaction, right? And
It
yeah,
releases hydrogen ions.
there you go. Right? So acids, good job. Acids are proper definition, right, which you need to know, are proton donors, right? So yes, they release hydrogen ions or protons, right? Saying hydrogen ions or protons is the same thing, because a hydrogen ion has lost the only electron it had, and the only thing this guy is a proton, right? So acids are proton donors. So whether it's HCl or whether it's methanoic acid, right, they're all going to give protons. A strong acid such as HCl, right, undergoes complete dissociation, right? So as many molecules of HCl there are, right, it will give up all of its protons. So, right, you have a one-way in aqueous, obviously not liquid HCl, but aqueous in solution, and so you're
But
getting
HCl
H
can
plus
be
and
a
Cl
gas.
minus. Hmm?
HCl can be a gas as well. No?
It could be a gas depending on the conditions. Yes, it could be a gas, right? Mostly we're dealing with it in its aqueous, you know, I wouldn't use the word state as not like a physical state, but it's aqueous form. Weak acids such as methanoic acid, right, undergo partial dissociation. So that means that this guy, not all the methanoic acids are going to give, right? So first of all, the hydrogen that's being lost is from the functional group, right? One thing to keep in mind, it's not the hydrogen that's, with the rest of the carbon chain. In this case, there isn't a carbon chain, but it's not that one. The other thing is that the reaction is reversible. So with weak acids, this is a reversible reaction. Not all the methanoic acid molecules are going to give up their protons, and the ones that do can recombine and form the methanoic acid molecule, right? So not as many protons are available with weak acids, and so, right, the reactions are not as strong and not as energetic, right? And they don't go undergo the entire range of reactions that other acids, mineral acids, and strong acids do, right? Even within mineral acids, you've got strong and weak acids, but compared to organic acids, yes, in general, mineral acids are stronger. So, do you guys recall all of this? We did talk about it, right? So, just as a recap.
Yes.
Now, right, carboxylic acids are weak, right? Nothing to be ashamed about. What are the reactions that they undergo? So, one of the acids is ethanoic acid, right? And ethanoic acid is one that is found in vinegar, right? So vinegar is actually, in fact, ethanoic acid is vinegar, right? So it's carboxylate, it's an organic acid, the vinegar that we use in our foods. And so it can react with an alkali. And remember, alkali is a soluble base, and it can give you a salt plus water, right? And so basically, what we're getting over here is a neutralization reaction, right? And the formation of water is important for neutralization, right? Because the definition is the H and the OH, they combine to give you H2O. So what does that look like? It looks like this. You've got ethanoic acid, plus sodium hydroxide, and that gives you, okay, now pay attention to the name, right? It's going to be a sodium salt. Remember preparations of salts, right? So it's going to be a sodium salt. So we're going to write sodium. And so what's the next time? Normally it would be sodium chloride or sodium sulfate or sodium carbonate or something over here. Right now we're dealing with, depending on whatever acid we use. So in this case, it's an organic acid. And so we take, okay, it's ethanoic. And so we write ethanoate. And so this kind of naming, right? Any you take any acid, so I'll come back to that, right? It could be methanoate, it could be propanoate, it could be butanoate. So the way you name it, right? Understand that. Plus water.
Only in the case of sodium.
No, it could be potassium ethanoate.
Okay.
You had potassium hydroxide, right? You had ammonium hydroxide, becomes ammonium ethanoate, right? So the alkali part comes first, and then the acid part, and that's the same as we did neutralization reactions earlier as well. The alkali, in the naming, the alkali part came first, and the acid part came, right? So we had potassium chloride, from potassium hydroxide and hydrogen chloride. We had sodium carbonate from sodium hydroxide and carbonic acid, right? Or magnesium sulfate, or whatever the reactions we had, right? So the metal part, or uh, the cation part, let's say, right? Because you've done electrolysis. So the cation, the positive ion comes first, the negative ion comes next, the acid part comes next, the base or the alkali comes first in the naming. So what does this look like in terms of its chemical formula? You have CH3, COOH. So you got your 2 carbons over here. And this guy is aqueous.
Why did we wrote like COOH?
This is the functional group of the acid, right?
Like, are we talking about alcohols over here?
This is a carboxylic acid.
Okay.
This guy, the functional group, right?
Okay.
This part. Actually, in this case, this part, ethanoic acid. Okay, so this part, the functional group of carboxylic acids, are written as COOH in the molecular formula. So you've got that plus NaOH, and that's also aqueous. And so what you're getting is CH3 COO, and I told you that the H is the one from the functional group, right? So that's what's making it acidic, and so it's lost that, and so you're getting an A over here, right? Plus H2, right? This is also aqueous, and this is a liquid. Now the only thing different over here, right? If this were sodium chloride, you would have written it as NaCl. If this were potassium sulfate, it would have been K2SO4, and so the metal part in the molecular formula would have been coming in first. In this case, the metal part, or the base part, or the cation, is coming in after the organic molecule, right? The naming, the way you name it is the same. The way you write it out in the molecular formula is a bit different, right? So just keep that in mind. So that's one reaction that these acids undergo. As for the naming, as I mentioned, right, we have, if you've got methanoic acid, and so the salt it will form is, so you take the meth part, meth plus, in fact, methane plus O8, right? So methanoate. Similarly, we did ethanoate, so propanoate and butanoate. Right, pentanoate, hexanoate. You right get the point. So that's how we're doing the naming. Any questions?
No.
No, sir.
Okay. Then I'm missing anything? No. So you've got ethanoic acid with sodium hydroxide. Then the acid can also react with metals and carbonates, right? So two separate reactions. In the case of metals, for example, we're going to react it with magnesium and we're going to get a magnesium salt out of this guy. So if we recall, right, acid plus metal gives salt plus hydrogen, right? And so we have ethanoic acid plus magnesium. And so what's the salt we're going to get out of this? Can you give me the name?
Magnesium.
Yeah, it's going to start with magnesium and then
Ethylene. What? How is it pronounced?
Sobia, how's it pronounced?
Ethanoic acid.
No, no, ethanoic acid. What will the name of the salt be?
Magnesium. Ethnic.
Ethnic. Look at this.
Ethanate.
Eth-
Noate.
ethanoate.
Yeah.
Right? These guys aren't eating. No ate. Right?
Yeah.
They're not very fond of eating. So methanoate and propanoate, none of these guys are eating. And hydrogen gas. What does it look
Like you
like?
said, there would be H2.
Huh?
You said like there would be H2 earlier.
H2.
H2O, water.
For for this reaction, right, with an alkali, over here you're reacting it with a metal. So if we actually go
Okay.
back and right, this is a very standard reaction for an acid with a metal. This is not a neutralization reaction. The water thing I mentioned was for neutralization reactions. CH3COOH plus magnesium. So this guy's going to be solid. This is aqueous. Right? And to make life easier for you guys, right? There are two molecules of that. And what we're going to get, we're going to get CH3COO, the whole thing twice Mg, so that's magnesium ethanoate, and this guy is aqueous plus H2 gas. Okay, now this looks scary, but just think of this as MgCl2, right? So the CH3 COO, what's the oxidation number? It's only -1, right? It's like an OH minus, kind of, right? Not the best comparison, but just like the charge is the thing that, right? So just like you got MgOH twice, which is obviously an alkali. In this case, this is salt, right? Cl obviously has a single negative charge, and so you got MgCl2, right? And so this whole thing twice, it's similar to MgCl2, right? So that's just with playing with the oxidation numbers or adjusting the oxidation numbers. Okay.
Yes.
Okay, next up, I think I'll just move to a new page. Right, is acid plus carbonate gives you a salt, carbon dioxide, and water. And so once again, we've got ethanoic acid. Again, this could be any of those. We're just sticking with ethanoic acid. It could be methanoic. Plus we have sodium carbonate. Right, so sodium carbonate itself is a salt. We're going to get a new salt. We're going to get sodium. What will the name be again? Sodium
ethanoate.
ethanoate. Now the good thing is there's no oral exam over here, right? And so you won't be asked to pronounce it. You just need to know how to spell it properly. Sodium ethanoate,
Carbon dioxide.
right?
But like we don't have oxygen over here.
We do not.
Then how are we getting carbon dioxide? Like from the atmosphere?
No, from the carbonate. This
Okay.
is Na2CO3, right? So you got CH3, COH plus Na2CO3 is going to give us CH3COONA, right? Because this is the oxidation number for this whole thing is -1 and sodium is +1, so they're happy together just like that. Plus CO2 plus H2, right? And so this is aqueous. This was actually a solid. This is going to be aqueous. This is going to be gas, and this is going to be a liquid, right? And to balance it out, you've got two of these guys and two of these guys, right? That balances the carbons and everything and the sodium as well. All right, so this is a very standard reaction for acids. If you just go back and like I'm not going to flip back right now, but if you just go back to the chapter of acids and you take a look at all the reactions, or even the chapter of metals and take a look at all the reactions, then right, this is what we've done earlier. The only difference is right now we are dealing with organic acids, carboxylic acids. Earlier on we were talking about sulfuric acid or carbonic acid or nitric acid or hydrochloric acid or all of those guys. Okay.
Yes.
Now, because it's an acid, right, you can use it in the typical acid reactions, right? So they will, as we've seen, right, these guys undergo typical acid reactions. And right, they also obviously cause a change in color with indicators. So if you take a blue litmus paper and you dip it into an acid, it will turn red.
Yeah.
Right, just an example of one indicator. All right, any questions about that?
No.
Okay. The next thing, and perhaps the last thing for this class, right, I might not be able to cover, definitely won't be able to cover condensation polymerization, right? So that will move on to next class. But right? We still have time for this. And we are going to talk about the last homologous series, the last organic family in the syllabus, and those are esters. Okay, now how are esters formed? They are formed via reactions between carboxylic acids and alcohols. Right, so you take a carboxylic acid, you take an alcohol, you react them together, and what you get is an ester, right? And this reaction is carried out in the presence of a few drops of concentrated sulfuric acid as a catalyst. So few drops of concentrated sulfuric acid, I'm writing that molecular formula as catalyst. So what do we have? We have, for example, our friend ethanoic acid, and we are reacting it with ethanol. And what we're getting out of this, it's a reversible reaction. Keep that in mind, right? Arrows go both ways, half arrows going either way. And you've got concentrated H2SO4, so that's a catalyst. And what you're getting in this case is ethyl ethanoate, which is the ester, and water. What does it, huh?
Athlete. How is it pronounced?
Ethyl ethanoate. Now the ethyl part, if you recall, I don't know how far back I'll have to skip, but I told you that if you have that, you've got methyl, ethyl, propyl, butyl, right?
These are all alcohols. Yeah.
No, those are the right, organic groups with a hydrogen removed,
Okay.
right? Anyway, let's take a look at this without going into specifics to confuse. You know, the easy thing is you just, the guideline is given in the text, and I'll put that on the whiteboard and explain it to you. So what you need to just know is how to name them. So even if they give you something unknown, as long as you know how to name it, you'll be fine, right? Just like I told you over here how to name these salts, right? You take the base or the metal or the cation part first, and then you take whatever acids, so methanoate or propanoate or butanoate, you add that name later, right? So as long as you understand how to go about naming them, whatever they throw at you, you should be able to handle. So as far as the chemical equation goes, you've got CH3COOH, and so that's aqueous, plus C2H5OH, right? And that's also aqueous. You got the reversible reaction, and what you're ending up with is the CH3COO, so that's the ethanoate part, right? So this guy has lost just a hydrogen, and the alcohol, so what you're losing, how are you getting the water? You're losing the hydrogen from the acid, you're losing the OH from the alcohol, and that's how you're getting the water. So when you lose the OH, what are you left with? Right, C2H5. So you add that over here, right? And this guy is aqueous plus H2O, which is a liquid.
Okay.
Now, before going into the general rules, so this process, right, is called ester esterification, right? We look at the link between these two guys, which is called the ester link. And they have the general formula, right? Stay with me. CnH2n plus 1, C double bond O, right? So that's the acid part. Then you've got C X H2X plus 1. And so this is the acid part, and this is the alcohol part. And right, the general formula will come in handy if they just ask you to, in words, react this and this, right? For example, they go, oh, show me a reaction between propanoic acid and butanol. And you're like, okay, what do I do? And so propanoic acid means that there are 3 carbons in this guy, and keeping in mind the functional group, N equals to 2. And so you get, okay, so C is 2, H2N plus 1 is 5, COO, and then butanol. So in this case, X, right? These are 4 carbons. And so you're getting C4 and H2 plus 1, right? That's H9. And so this is the molecular formula for a reaction between propanoic acid and butanol.
Okay.
If they give you the molecular formula for them individually, how do you go about solving that? So you've got C2H5COOH plus, right, butanol, so that's C4H9OH. And so, okay, fine. So how do I do this? So 2 things to keep in mind. The first thing, you're going to get water as a product. And as I told you, the water comes, right, the hydrogen is lost from the acid, the OH is lost from the alcohol, right? So those two are going to come together to give you H2O, right? So you've got the plus H2O part over here. What about the rest? Just put the rest together, right? Simple. So you've got this guy after, having the hydrogen from the acid react. And so you've got C2H5C double O, and then you put the alcohol part, which is left after, losing the OH. That's C4H9, and you're done. So it's pretty straightforward if you look at it that way.
Yeah.
So if they give that to you in words, you know how many carbons each has, you know the N and the X. I mean, you put this X, you put this as P, you put this as, I don't know, M, whatever you put, one like R, whatever you want to put it as, right? Doesn't matter. This is basically shows the variable, right? And so you can figure it out that way. And if they're giving you the molecular formula, it makes it even easier. The naming, how do we go about naming these guys? That's right, that might seem a bit more tricky. And so the alcohol part comes first. So with the naming of esters, right? And so whatever alcohol you have, right, whether it's methanol or propanol, right, what's happening with these guys? This guy is CH3OH, and this guy is C3H7OH. Right? And so I told you when we're talking about alkanes that if you lose this, right, all you're left with is CH3 or C3H7, right? Or I told you with alkanes, if this was methane, it was CH4, right? And you got CH3 out of it, or this was C3 and H8, so that's propane, and you got C3H7 out of it, right? Instead of methane, you're going to take the meth and you're going to add the YL and you're going to get methyl, right? In this case, you're going to get the prop plus a YL and you're going to get propyl, right? So these are the alkyl. They're not a separate organic group. They're just, right? What they are is this. You've got a carbon with 3 hydrogens, and what they're showing is, right, that there's this one bond that carbon can still make, and so it can react and have something else come in over here, right? Basically this is what it signifies. So when the OH is lost from the alcohol, right, it used to be this, so that's methanol, but now the OH is gone, and so there's one bond vacant for carbon. And so however many carbons you have, again, right, meth, eth, prop, bute, pent, and hex, I've told you up till hex, that's 6 carbons. The book only takes you up till 4. And so whatever you have, you add YL next to it, and so you get methyl and propyl. So the first name, right, the alcohol part comes in first. So whatever alcohol you have, in this case, let's name this guy, you had butanol, right? And so how would that name be over here, right? Are you guys following?
Yes.
Yes.
Right? So given this molecule that we've created over here, how would we name this, right? We had propanoic acid and butanol. In the name, the alcohol part comes first. So what are we going to take from butanol to put into the name of this ester?
Can you please repeat that again?
When naming esters, the alcohol part comes first. It comes named like an alkyl, right? So methyl or propyl, however that's pronounced.
YL will come first,
Yes.
yes.
So you had butanol over here. So
Yeah.
how would you use this in the name?
Butyl,
Butyl,
butyl. Sorry.
right? And so this guy is coming first in the name. So the compound we made is butyl something, right? Let's look at what the something is. The second part is the acid part. Okay.
Yeah.
Yes.
So acid part second, right? And that's going to be as an O8, right? Which is basically the anion, right? That's the name you give to the anion formed after losing the proton from the acid, right? And so explain that. And so we had propanoic acid. So how are we going to name that?
Propanate.
Propanoate, right? And so this is going to be butyl propanoate. And so this molecule is butyl, right?
Propanoate.
Propanoate. In terms of molecular formula, right? Now again, not to confuse you, when naming esters, the alcohol part comes first, the acid part comes second. Writing the molecular formula, what we can see is that we've written the acid part first and the alcohol second. So just something for you to keep in mind. Sometimes when we break things down into what we believe to be easier steps, they actually sort of start seeming to be confusing. So
Yeah.
right. I mean, obviously for me this is pretty straightforward, but right, since this is your first introduction to all of this stuff, it might be a bit confusing, especially the naming and all of that. Right, one's coming first and the other's coming second, all of that. But if you just give yourself a bit of time to process it, I'm confident that it will solve out better. Okay. I'll show you the book, right? They've given some esters over there, a table with some esters. Right, can you see that?
Yes.
Okay, let me zoom in a bit. So we've got ethyl ethanoate, right? So the ethyl part is coming from ethanol, which is the alcohol. The ethanoate is coming from ethanoic acid, right? And as a displayed formula, this is what it looks like, right? So this is again, right, in terms of writing its molecular formula, the acid part comes first, and in its displayed formula, also the acid part. This is the acid part. Right, so you've got the first carbon with 3 hydrogens and the second carbon, one with the double bond O. Right, as far as we're concerned, you don't touch the double bond O, right? Then the other oxygen which had the hydrogen with it, which is lost, right? So that's the acid part, and that's where the alcohol is joining in. So the alcohol has lost the OH group, and now, so that's right. I told you that this carbon has a bond that it's willing to make, and so it makes that single bond with the oxygen. So this is ethyl ethanoate, and just to write this part, the C double bond OC, right? This is called the ester link. Right, so if I just take you back, like we will come across it when we start talking about like the last part of organic chemistry, which is condensation polymerization. So right, just to highlight that this C double bond O and then this OC, so this COOC, this is called an ester bond or an ester link. Okay. Then you've got propane 1-ol, so propanol basically, and methanoic acid. And so to name this, you're going to get propyl methanoate. And the methanoic acid in the molecular formula, the displayed formula, they haven't given the displayed formula. Well, yeah, this is not the complete displayed formula, it's just a molecular formula, right? And the sorry, the structural formula, this is the displayed formula. I'm talking like the structural formula, this is not the complete structural formula. And so in the displayed formula as well, the acid part comes first, so that's the methanoic acid part, and this is the propanol part, right? And this is what an ester molecule looks like. And finally, you've got methanol, so you're going to get methyl, and then butanoic acid, so butanoate, so methyl butanoate, right? And so it's a 4-carbon acid, so you've got those 4 carbons, including the carbon from the functional group, right? And then methanol, so that's just a single carbon, you've got that over here. Hopefully that makes it simpler to follow and understand what's happening. And then they just tell you that many esters are occurring naturally, and they have, right, the fragrance that you get from fruits or flowers, right? And those are esters chemically, right? Those are esters, and they're also used in perfumes and food flavorings, right? So they probably taste good as well, right? They smell good, so they're good chemicals for us. And then fats and oils that occur naturally are chemically they're esters, right? And animals and plants use them as energy stores. And esters, the ester link is also the same as something called PET, right? And so when we talk about condensation polymerization the next time, right? You'll see what PET is, but they're telling you, okay, fine. So there's this thing called PET and or PET, right? It's also called PET. So, right, that also has the ester linkage. Any questions?
Nope.
Sure.
Yes.
Okay, then I'll see you guys next time, inshallah.
Allah Hafiz.
Okay, Lafis.
Do review this, right? Give yourself time to process it. Hopefully, it will sort out.
Okay.
All right.
Allah Hafiz.
Allah Hafiz.